Albert Einstein once said, "I have no special talents, I am only passionately curious." It's a surprising claim from a man whose name became the gold standard for intelligence. But what if that's exactly the lesson of his life? That the curiosity to keep looking at everyday things like a compass or a beam of light can reveal the hidden laws of reality itself. His story teaches us how ordinary wonder can lead to extraordinary results. Imagine a small boy holding a compass in his hand. The needle quivers, then steadies, always pointing north. To most children, it is a toy, something that spins if you shake it and settles when you stop. But for this child, it becomes a puzzle. How can a thin piece of metal know where north is? What guides it when nothing appears to touch it? In that moment, the ordinary turns strange, and the strange demands an answer. For young Albert, the compass was not about finding direction on maps. It was proof of hidden forces, invisible yet powerful, shaping what seemed solid and simple. If you picture the earth as giant machinery, the needle was like a clue left behind, showing that something deeper was at work beneath the surface. The idea that nature held secrets below the reach of sight planted itself early in his mind. Most classrooms of that era prized quick memorization and obedience. Teachers wanted fast answers, strict repetition, and neat rows of facts. But this boy's mind wandered. He asked what lay behind the answers, why rules existed, and whether they could change. Instructors, seeing his slow speech and deliberate manner, thought he lagged behind. The word slow followed him into hallways, even into the judgment of adults who should have been guides. Yet being told he was behind masked what was really taking place. By refusing to parrot lessons, he was doing something schools rarely rewarded, forming his own questions. If the compass pointed north without rope or chain, what other hidden pulls might shape the world? Where else in daily life might unseen lines of force operate? The label of poor student hid the fact he was rehearsing the skills of discovery, patience, doubt, and independence. His father's work meant the family moved more than most. With each new town came a new classroom, a new set of standards, and often a new language. To a child already resistant to rigid teaching, this created constant tension. He had to adapt, time and again, to rules that shifted with each city. This could have broken focus in another child. For him, it trained agility. Every move meant absorbing a new system, while privately maintaining his own way of questioning. As we watch his story unfold, that early compass stands as a symbol. The magnetic field that shaped its needle stretched far beyond his childhood toys. It was invisible, consistent, and patient, just as he would be in following problems that no one else thought to pursue. What looks like play becomes practice, and practice grows into method. Many myths grew later, stories saying he failed subjects or barely survived school. These tales exaggerate, but they stick because they match the image of a rebel. The truth is more practical. He mastered what mattered to him and ignored what felt empty. Teachers mistook that selectivity for weakness. In reality, it was choice. Like the compass refusing to point down or sideways, he pointed steadily toward what mattered most in his own eyes. Think of the needle again. Held in your hand, it twitches at first, unsettled by nearby metal or a change in balance. Then it steadies. Albert's schooling followed the same rhythm, at times disorderly, pulled by family moves or critical teachers, yet always settling back toward curiosity. That pattern of disruption and return mirrored the later conflicts of his adult life. Even when distracted or dismissed, he returned to questions of light, motion, and hidden order. What made his curiosity different was how seriously he treated simple things. Many children wonder why the sky is blue or why shadows change with the sun. For him, such wonders never faded into background noise. They sharpened. The compass was first. Soon came questions about beams of light, about what a person would see if they could ride alongside one. To most teachers, they were distractions. To him, they were the center of learning. Every move his family endured widened this effect. Imagine a boy crossing into another region where classmates spoke with different accents and rules of schooling shifted. Each transition underscored the idea that authority could be temporary, not absolute. If rules of grading could change when geography changed, then perhaps natural laws might also hide layers waiting to be discovered. Out of this instability grew his independence. This independence brought friction. Sitting still for drills frustrated him. Memorizing dates or declaiming passages bored him. Yet he spent long stretches tinkering alone, studying mechanical objects with the same quiet intensity he once gave the compass. While parents worried about his slowness, he was in training, not in the school sense of marks and timetables, but in the patient habit of thinking problems through without relying on others for guidance. From our view today, it is easy to see how thin the charge of failure was. What teachers dismissed as distraction was in fact focus turned inward. Curiosity that did not obey lesson plans looked like inattention, but it produced the soil where real questions could grow. By setting aside received answers, he was already practicing science's most important move, challenging what seemed certain. The reputation of a bad student faded later, but the misunderstanding speaks volumes. It shows how institutions prefer conformity, yet genius often looks like refusal. The boy with the compass could not stop asking why. His teachers wanted end results, but he wanted causes. That tension explains much of what followed in his life. Debates with colleagues, conflicts with accepted theories, even his restless moves between countries. In the compass experience, we see the seed. A hidden order directs what looks like chance. A child looks closer while others look away. And once seen, the presence of invisible structure becomes impossible to forget. It is not just a stage of childhood, it becomes a lifelong posture. If you imagine yourself holding that same compass, you can sense what he sensed. The stillness actually hides motion. The silence hides power. What appears empty is in fact charged with unseen lines, shaping matter itself. For Albert, this first lesson never loosened its hold. To this day, physicists still unite around the idea born from such moments, that the world is not as it appears, and the invisible shapes the visible. This is why that early reputation as a failed pupil reads differently now. He was never failing. He was learning in a way the system could not measure. Every time the compass needle swung back north, it confirmed a truth. Independence matters. The label of disobedience or slowness misses the point. His teachers looked at recitation. He looked at reality. The compass became not just an object, but a clue to method. Follow invisible signs. Trust steady rules beneath surface chaos. And never forget that the universe hides forces waiting for discovery. Those rules guided his imagination toward deeper questions. What bends light? What anchors time? What holds matter together? So the story begins not with equations, but with a boy staring at a quivering needle. We can trace almost every later breakthrough back to that first moment of wonder. A simple object forced him to shape a habit. Never accept appearances, always test what lies beneath. And with that habit, the path was set for a lifetime of asking why the universe behaves the way it does. What kind of 16-year-old walks away from a nation and becomes stateless? That choice sounds reckless today, let alone in an age when citizenship meant access to schooling, work, and protection. Yet Einstein cut himself free from what was expected and stepped into a stage of life with no clear guarantees. At the core was the question of military duty. To hold German citizenship meant service, and to serve meant bending to discipline that allowed no room for resistance. For a boy already marked as difficult by instructors, such a future felt like a trap. Refusal was not safe. But compliance threatened to crush the independence he had come to rely on. Between pressure and freedom, he chose uncertainty. Without a state, you risked being treated as no one. Basic documents, travel rights, even the chance to study, each became harder to secure. At 16, he held a passport to nowhere. Practically, it meant vulnerability. No government carried his case. No institution felt duty to support him. Such a move could have ended with broken opportunities rather than new doors. Then came Zurich Polytechnic, one of the rare institutions willing to admit someone without a national bond. Entrance tested both mathematics and physics, yet it also favored determination. Here was a path forward, slim but open. To Einstein, the place stood like a bridge suspended between isolation and possibility. Walk it, and science might open. Fail, and choices collapsed. The school carried its own weight of expectations. Professors pushed students through formal drills, structured courses, and precise memorization. Once again his manner clashed with those measures. He absorbed what he valued, skipped what he judged trivial, and kept exploring his own problems apart from lectures. That selective approach drew frustration from teachers who marked him as careless. Yet he continued, balancing between discipline imposed from above and curiosity rising from within. To understand the tension, think of a locked gate on a canal. Water behind it wants to press forward. Boards fixed across demand, order, and timing. The gate can channel the flood or obstruct it. In Zurich, the rigid courses acted like those gates. For many students, they structured flow, controlling the pace. For Einstein, they sometimes blocked, producing conflict. But pressure builds behind wood. Eventually, the water carves its way through. Amid that structure came an unexpected form of release, companions who shared questions restless enough to break schedule. He encountered Mileva Maric, a fellow student eager to engage in mathematics and physics. For him, this was more than social comfort. At last, discussions in which probing doubts, wild notions, and deep calculations had space. A circle slowly formed, peers who asked as he asked, resistant to passive repetition. In these exchanges, independence became reinforcement rather than isolation. While official instruction judged him uneven, within this private network conversation strengthened his ability to question, refine, and push further. You could say the gate still held tight, but channels in its wood widened, water passed, and with it new energy. The earlier choice to abandon all ties now appeared different. At the moment of refusal it had seemed destructive, the loss of citizenship, the stripping of protection. But forged into that loss was unusual freedom. With no duty to the uniform, no expectation of loyalty to empire, his path turned toward ideas with fewer chains. Saying no to one life created capacity to say yes to another. Yet the danger was always near. Faculty reviews noted his inconsistent habits. Bureaucratic records marked his lack of nationality, the wrong judgment, the wrong rejection, and stability could vanish. To persist required steady resolve, the same kind of persistence later seen in scientific puzzles. The choice of statelessness had been one risk, staying committed through years of formal education while holding to that independence was another. This is where the story sharpens. Many imagine genius as a flood of effortless insight. Here we see calculation of a different sort, the gamble to strip away social safety for intellectual breathing space. Imagine standing on a mountain ledge. Behind is drill command and forced service. Ahead is thin ground, uncertain weather. Step forward and you might cross, pause, and you slip. He kept walking. Within the Polytechnic halls, other contradictions grew. Professors valued tidy solutions written as instructed. He preferred questions written in his own framing. They watched for obedience. He sought patterns. Again and again the conflict repeated, rule versus independence. The setting could have broken him, but paradoxically, the clash honed his perseverance. To resist and still advance required tactical patience. He learned when to deliver the minimum expected and when to withhold energy for private investigation. The network of peers mattered here. Alone, resistance can feel like arrogance. In dialogue with others pressing the same problems, resistance becomes community. With Mileva and others exchanging notes, debating equations, and voicing skepticism, Einstein found his questioning was not unique. This confirmed that his way of operating was valid, even if institutions misread it. Step back and you see the transformation. A teenager once marked as slow, then condemned for abandoning country, now anchored in study. Yet still outside full conformity. From one angle, this looked like peril. From another, it revealed strength. The compass from childhood had shown him a hidden order beneath surface appearances. Now the act of becoming stateless showed him the power of holding to principle against overwhelming norms. Both lessons fit the same pattern. Trust what inner direction reveals, even under pressure. Think about what this means beyond his personal story. To live stateless is to walk without legal anchor. To endure structured courses while refusing full obedience is to risk academic failure. To link with peers instead of authorities is to build sideways rather than upward. These moves each carried cost, yet together they forged the posture of independent thinking. Science advanced later through that same stance, questioning laws once revered as absolute, following intuition when convention pressed elsewhere. The payoff of those student years was not grades on a record, but an environment seeded with alliance and dialogue. Ideas traded across study tables and quiet discussions shaped paths far beyond coursework. The rigid channels of the institution, irritating as they were, provided context against which independence showed its strength. Like water meeting rock, the clash created direction and force. So in the end, what looked like a dangerous loss, the shedding of citizenship, the risk of academic censure, became formative. It was not safety but freedom of the mind that resulted. By walking away from a nation, Einstein had unknowingly stepped toward a life in which ideas carried more weight than allegiance and curiosity spoke louder than obedience. Most people saw a dull office where inventions collected dust in dense files. Einstein saw something else. The patent office looked like a stopgap job, far removed from the lecture halls he once hoped to enter. Yet, from that modest desk, surrounded by stacks of applications on mechanical devices and electrical systems, he began shaping problems that would reframe our view of the universe. It mattered that he had been pushed aside by academia. Universities saw him as undisciplined, careless about formal obligations, not fit for a proper teaching post. So he took the position of examiner, reading other people's ideas, often far less ambitious than his own. On the surface, it looked like exile from science, but exile became fertile ground. The job required close attention to detail. He had to judge whether a new electrical switch or communication device was original, whether claims about synchronization or transmission held together. This process honed a sharp skill, breaking down complex machinery into first principles. Each day he looked at diagrams and text that demanded clarity about time, sequence, and reliability. While most would simply tick boxes, he treated the reviews like exercises in fundamental analysis. Think of it like a craftsman handed hundreds of locks, each with subtle changes. The craftsman must test every key, check every gear, make sure it will not jam. Over time, a map of all possible locks sits in their mind. The patent files did the same for Einstein. They confronted him with many ways humans tried to harness electricity and motion. Examining them gave him a library of possibilities, fuel for imaginative leaps. The tension sharpened. He knew he was overqualified, He was trained in physics, eager to explore theory, yet locked in a role that demanded bureaucracy. For many, this would drain energy. They might feel wasted, watching colleagues rise around them while they remained stuck. He certainly sensed that sting. But rather than let it wither into frustration, he used it as contrast. The monotony of repetitive files gave way to the relief of private thought experiments. In the quiet rhythm of the office, questions unfolded. If two clocks ticked far apart, how could we know if they truly kept time together? Telegraphy patents raised the issue. Signals had to synchronize distant stations. Behind the paperwork lay a deeper puzzle. What does it mean to say two events happen at the same moment, especially when light itself takes time to travel? That mundane administrative duty anchored one of his most profound investigations. Instead of seeing the desk as a prison, he transformed it into a laboratory of the mind. A mechanical signal across a wire could spark the question of how motion affects measurement. An attempt to improve communication could echo into debates about the nature of simultaneity. Without the grind of those reviews, he might never have sharpened his intuition about time and space. You can imagine the scene: files stacked, walls lined with cabinets, the tick of a clock marking hours in regulatory rhythm. On the surface, nothing dramatic. Yet in those hours his thoughts ran like currents under ice. Each application added a trigger. Each diagram suggested a scenario. By day he confirmed patents. By evening he turned them into questions that no examiner before him had considered. Now consider the irony. Universities withheld positions because he would not conform. They feared his untamed approach. Yet the very space denied him formal research posts, pushed him to the setting that fostered freer speculation. Without pressure to publish or lecture, he could follow personal interests. The desk, once symbol of rejection, became his shield against noise. Many described the job as safe but dull. Safe meant regular pay, modest respectability, a steady life. Dull meant routine, papers without spark. But hidden opportunity lay inside that paradox. Stability gave him time. Time gave him thought. Thought turned into insight. The trade was uneven, anonymity in exchange for freedom. But freedom mattered most. The method he built followed a pattern. First, he pictured a simple scenario: a train moving along a track, a beam of light chasing beside it, a clock seen in one place compared with a clock elsewhere. Then he pushed it outward, stripping away assumptions until the paradox appeared. Was simultaneity absolute? Did time flow the same for all observers? These questions crystallized not in rare laboratories, but on scraps of paper after office hours. Imagine working on repetitive tasks, but keeping a parallel track in your mind. The simple note in a file, signal sent, signal received, transforms into a model of moving observers and the speed of light. This was his habit. He recast bureaucracy as a stage for imagination. In this way, what others saw as drudgery became a disguised blessing. The conflict remained palpable. Colleagues advanced in universities, gaining recognition, while his writings lay largely unread at first. Rejection had placed him here. The temptation to see it as waste was real. Yet gradually the opposite became clear. The independence of the desk freed him from conforming to established thinking. Without lectures to deliver, he was not bound to repeat the old frameworks. Instead, he could question first principles without pressure. Pay attention to the pattern here. Childhood had given him the compass, proof that unseen forces ruled what looked ordinary. Student years had given him statelessness, proof that discarding conformity could open new paths. Now came the desk years, proof that rejection can create space. Each stage added a layer. Each apparent setback planted conditions for deeper insight. The patent files about synchronization were especially vital. They raised one unavoidable fact. To call two things simultaneous, you must define the signal that links them. Light was that signal. But if the signal itself obeys its own limit of speed, then simultaneity ceases to be obvious. In obsessing over telegraphs and electrical coordination, he glimpsed the key to reshaping time itself. From this process, daily monotony lit sparks. Files pushed him to imagine, imagination pushed him to challenge, and challenges led to questions that, about a year later, would explode into papers that no one in physics could ignore. It is easy to overlook the role of setting, yet here it stands. The quiet room of folders and stamps incubated revolutions in theory. Picture it again, the office, the still floor, the endless stacks. They looked like constraints, yet within them thought gained focus. Like light bending through a narrow slit, the constraints produced sharper patterns. Those sharp patterns eventually sliced through centuries-old assumptions about physics. So the desk, ordinary to most, ordinary even to him at first, became a hidden partner in discovery, not by inspiring grand visions directly, but by forcing him to think with exceptional clarity about coordination, motion, and time. Instead of killing creativity, the patent office became its launchpad. From those files, the framework of modern physics began to take shape. 4 papers, 1 year, the intellectual equivalent of 4 lightning bolts striking the same place. In 1905, while still working at the patent office, Einstein dropped ideas into physics that were so disruptive they reshaped the entire field. Each paper touched a different mystery: light, atoms, time, and energy. Alone they would have stood as major contributions. Together they marked a breakpoint, a year that entered history as his annus mirabilis, his miracle year. To grasp why, consider the state of physics just before that time. Light had long been described as a wave, explained by interference and diffraction experiments. Yet some effects resisted that description. Atoms themselves, the supposed building blocks of matter, were still under debate. Some argued they were useful fictions, a way to model behavior of gases, but not solidly proved. And then space and time, anchored by Newton for centuries, were assumed to be absolute, the unmoving stage where all other events unfolded. These puzzles were real, but appeared to belong to separate conversations. Few imagined that a single researcher could push into all of them within months. Einstein's first strike came in the spring, looking at the photoelectric effect. When light shines on certain metals, the surface emits electrons. Classical wave theory stumbled here. If light were only a wave, then increasing the brightness, no matter how low the frequency, should eventually push electrons free. But experiments showed otherwise. Only light above a threshold frequency could knock electrons loose, regardless of how intense the beam was. Einstein proposed something radical. Light behaved not just as a wave, but also as if it came packaged in discrete quanta of energy proportional to frequency. He later called them photons. This was not just a minor adjustment. It was an announcement that energy, the continuous flow described in classical physics, could arrive in packets. A beam of light acted like a stream of particles. That leap opened the door to quantum theory. Decades later, solar panels and sensors would embody this principle, converting photons into usable current. But at that moment, the claim was startling, hinting that nature's fabric contained graininess where smooth flow had been assumed. The second paper of the year tackled Brownian motion, the jittery movement of particles suspended in a fluid. Microscope users had long watched tiny grains dance randomly in water, but the cause was mysterious. Some dismissed it as quirks of the instruments. Others speculated hidden currents or life forces pushed the specks around. Einstein treated it systematically. He calculated that if matter was made of atoms, the constant collisions of molecules with any suspended grain would generate that irregular motion. He even showed how to measure the average displacement of the particle over time to estimate the actual size of the molecules striking it. This argument delivered a crushing blow to atom skeptics. Atoms were no longer philosophical speculation, but measurable entities, pushing other matter around in ways microscopes could confirm. The tiny bouncing of pollen grains became proof that matter consisted of countless unseen units in ceaseless motion. In connecting invisible collisions with observable motion, Einstein made the case that the atom was real. Within years, skepticism about atoms faded, and chemistry and physics embraced them as concrete building blocks. If the first two works nudged pieces of physics, the third shifted the foundation. Published in late September, this paper bore the straightforward title, On the Electrodynamics of Moving Bodies, but its consequences exploded conventions. Einstein asked, what if the speed of light is the same for all observers, regardless of motion? If this constancy is true, then the old assumption of absolute time cannot survive. The outcome was special relativity. Time can stretch or compress depending on the speed of the observer. Lengths can contract. Simultaneity, once assumed self-evident, becomes relative. Imagine two lightning bolts hitting opposite ends of a train. To someone on the platform, they may seem simultaneous. To someone riding inside, motion shifts the sequence. Both are correct, and there is no universal frame to settle the matter. This collapse of absolute space and time forced physicists to recognize a hybrid fabric, space-time, where measurements depend on motion. The ripple effects are enormous. Concepts like GPS, which relies on signals from satellites moving high above Earth, apply corrections from special relativity to remain accurate. Without them, your map would drift miles from reality. Such modern tools rely on equations born out of Einstein's patience in parsing what simultaneity really means. Then came the fourth paper, short but piercing. It asked whether inertia, the resistance of matter to being accelerated, connects directly to energy content. The answer yielded an equation simple enough to fit on a line. E equals mc squared. Mass is another form of energy, locked inside matter at rest. A seemingly small amount of mass corresponds to a vast quantity of energy once released, because the conversion factor, the square of the speed of light, is enormous. The idea spun consequences far beyond its page length. It showed that stars shine because mass transforms into light energy through nuclear fusion. It laid the theoretical basis that decades later allowed nuclear fission reactors and weapons. But at its root, it was a statement about matter itself. What had seemed solid and irreducible could be transformed, linking two previously distinct quantities, mass and energy, into a unified currency of the universe. What stands out about these four breakthroughs is not only their depth, but their diversity. They tackled unrelated questions: light's nature, matter's foundation, space and time, and mass and energy. Yet from a desk in Bern, in one intense year, the same mind bound them together. It was as if the walls between physics' scattered puzzles cracked at once. Scientists had to step into a landscape where certainty had dissolved. At the time, recognition came slowly. Journals recorded the work, but the ideas demanded a shift in worldview too large for immediate acceptance. Some doubted, some ignored, some debated fiercely. But gradually, experiments, photoelectric devices, Brownian analyses, tests of relativity's predictions, confirmed them. Piece by piece, Einstein's papers took root, not as speculation, but as foundations. To this day, each of those papers holds weight. Quantum theory would have been incomplete without photons. Atomic theory gained firm support from Brownian motion. Space and time bent into relative forms through special relativity. And nuclear science harnessed mass-energy equivalence. Looking back, 1905 is not just Einstein's miracle year. It is a moment when physics shed an older skin. Questions once thought settled became open again. Answers that appeared permanent dissolved. After that year, science no longer asked only, what are the rules of motion? It asked instead, how deep do those rules run, and how much of what we take for granted is only apparent? The shift was permanent. After 1905, there was no going back to Newton's certainty of fixed absolute space or to the smoothness of continuous waves. Light had a dual life. Atoms carried undeniable reality. Time itself bent with speed, and energy and mass became two faces of one coin. The framework had changed. Einstein did not just add to physics. He changed the questions forever. Imagine the sky darkening in the middle of the day. The moon passes in front of the sun, light fades, and stars appear in a sky that should still be blue. In that eerie silence, nature offers a test so rare it may not come again for years. Into this moment enters one of the boldest claims ever made in physics, that space itself can bend, and that even the path of starlight will curve as it passes by the sun. When Einstein first proposed general relativity in 1915, many physicists accepted it as clever mathematics, but few were ready to let it displace the weight of Newton. Newton's picture had held for centuries. Gravity meant attraction between masses, a force pulling objects toward one another through empty space. It was direct, clear, and measurable. Einstein replaced that with a stranger vision. Mass did not pull, it shaped. Think of space and time as a stretched rubber sheet. Place something heavy, and it sinks the sheet, curving it. Objects move not because they are pulled, but because they follow paths laid out in this warped surface. The decisive difference was light. In Newton's view, light, lacking weight, traveled straight. In Einstein's view, light would be compelled to curve along the dents in space-time created by a massive body. If the sun deflected starlight, an observer during an eclipse might see stars appear slightly misplaced. Their light bent as it grazed the sun's edge. No ordinary day sky would allow the test. The sun's glare would overwhelm distant starlight. Only an eclipse could strip that glare away. By 1919, the opportunity arrived. Astronomers prepared instruments, timed exposures, and planned expeditions. The idea was simple, yet delicate. Take photographs of stars during the eclipse, then compare them to plates made at night when the sun was elsewhere. If relativity was right, the positions near the solar limb would shift, light paths bent by a tiny but measurable angle. If Newton was right, no such bending would occur. Waiting for a total eclipse carried risk. Clouds, bad equipment, or miscalculation could erase months of preparation. But the astronomers pressed forward, aware that one event could overthrow or uphold centuries of understanding. They were not merely recording shadow, they were weighing two worldviews, one rooted in tradition, one startlingly new. The morning came. As the moon swallowed the sun, telescopes fixed on fields of stars, photographic plates captured their light in that fragile window of darkness. When the eclipsed sun revealed itself framed by constellations it normally hid, instruments gathered the data Einstein had staked his theory upon. After the eclipse ended, the slow process of measurement began. Plates were developed, positions checked, uncertainties assessed. Scholars compared the coordinates taken in full daylight to the positions at night. Careful alignment showed something remarkable. The stars, when their light passed near the sun, had appeared slightly displaced. The deflection matched Einstein's prediction. For the global scientific community, the result hit like shock waves. Centuries of Newtonian certainty cracked. When newspapers reported the findings, language was dramatic. Headlines claimed that Einstein had overthrown the model of the universe developed by Isaac Newton nearly 250 years earlier. For readers outside science, the message rang clear. What was once unshakable law had been overturned by a new vision. This was more than a measurement. It was a public rebirth of reality itself. Readers who had never read an equation saw in headlines the death of one universe and the birth of another. Space and time, once imagined as rigid, had become flexible stage material, bending under the presence of mass and energy. The idea shocked the imagination. Were even our measurements of time itself open to distortion? Einstein, who until then remained known mostly within circles of physicists, suddenly stood in newspapers around the globe. His untidy hair, his reflective gaze, and his unusual refusal to dress the part of the authority figure all became symbols. Overnight he transformed into what some would call the first modern celebrity scientist. The relativity he had built from equations now circulated as part of human culture. But what made the impact so deep was the contrast. For years, relativity had existed only in journals, understood by a few, doubted by many. In an instant, an astronomical event available to anyone with a newspaper confirmed it. The delay between theory and recognition collapsed. Humanity witnessed a rare moment where abstract prediction met sensory proof in a way that ended debate. It's hard to appreciate how radical it felt from inside that era. Newton's universe was not just science, it was part of how the West told its story of mastery over nature. Ships navigated seas by Newtonian tides, guns fired cannonballs with Newtonian arcs, planets orbited by Newtonian rules. For centuries, to doubt Newton was to doubt the foundation of reason itself. Yet in one eclipse, starlight bent to Einstein. This moment reshaped not only physics, but also the role of scientists. Einstein became someone the public wanted to hear on matters outside his discipline. He was asked about politics, philosophy, human values. He became a voice not just of theory, but of worldly intellect. That cultural position followed naturally from the shock of 1919. If he could tell us that space and time bend, perhaps his voice mattered on questions of war, nationalism, or peace. Consider the symbolism. The universe itself seemed to have staged a drama. The sun, normally too bright to test, was veiled by the moon at the precise time measurements could be made. Stars, normally absent from the day sky, emerged to offer their verdict. Nature itself stood as the experimenter, confirming or refuting the claims of theory. The verdict was clear: relativity held, Newton's certainty had limits. The announcement fueled fascination. Suddenly, newspapers ran features attempting to explain the counterintuitive world of relativity. Cartoonists mocked and admired it, novels hinted at it, discussion groups debated it. Einstein's name became shorthand for brilliance. His theory, an emblem of the strange, modern age, where even space was unreliable. For Einstein personally, this shift was dramatic. From a patent clerk and overlooked lecturer, he found himself thrust into international acclaim. Recognition flowed quickly. Universities and institutions offered him positions. Invitations to speak multiplied. He became seen as a standard-bearer of intellectual progress, just as the 20th century entered upheaval after war. But recognition carried weight. No longer able to work in the quiet rhythms of obscurity, he now inhabited a stage where every remark might spread across newspapers. Fame altered his relationship to physics itself. Yet the eclipse had made its mark. It was the threshold moment when physics became public story, and Einstein became legend. Think of it this way: a fleeting shadow crossing the earth made visible what equations had only whispered. Light that had traveled millions of years, bent by a fraction of a degree, near the sun told humanity that even empty space is not empty, but alive with curvature. That bending reoriented how we measure, how we navigate, how we imagine the universe. The eclipse of 1919 proved that Einstein's vision of general relativity was not abstract poetry, but measurable law. And in proving it, science gained a new star, not just in the sky, but in the figure of a physicist whose name joined the front pages. Einstein stepped out of theory and into legend. How does a scientist of peace end up writing the letter that leads to the atomic bomb? That question follows Einstein through one of the most difficult turns of the 20th century. To understand it, we need to begin with his earliest stance on war. When the First World War broke out, many German intellectuals rushed to justify the conflict. A document known as the Manifesto of the 93 gathered signatures from scholars and writers to show loyalty to German militarism. Einstein refused. Instead, he supported an alternative declaration, the Manifesto to the Europeans, which called for a shared European culture, not competition through weapons. Even then, in the middle of patriotic pressure, he marked himself as a pacifist. To him, war was not an answer, but a failure of imagination. That refusal was not without consequence. While others gained status for supporting the government, Einstein's position cost him favor, yet the choice also defined him. He was willing to stand outside the chorus in Germany, raising a voice for peace in a society that equated dissent with disloyalty. His phrase for war was direct and unsparing. He described it as a disease, not a cure. Then the 1930s unfolded. Germany shifted under the rise of Nazism, and that anti-war stance, combined with his Jewish heritage, placed him in direct danger. Universities pushed Jewish academics out. Propaganda turned science itself into a nationalist weapon. Einstein not only rejected that tide, but abandoned German citizenship altogether. By 1933, he and his wife fled, landing in America, where he accepted a position at the New Institute for Advanced Study in Princeton, New Jersey. The move stripped away more than paperwork. It meant breaking with the state that had formed him. It meant watching friends and colleagues disappear under a regime that hunted difference. To see ideas turned into tools of oppression left a deep weight he carried into his American years. In exile, his pacifism remained intact, but the ground had shifted. For the first time, a threat existed that could not be ignored from the safety of a study. The tension rose as physicists realized the new scale of possibility hiding in atomic structure. Nuclear fission, splitting a heavy atom, could release energy far beyond chemical reactions. And with Nazi Germany arming at speed, the idea that its scientists might harness such power looked conceivable. This was not a distant theoretical game. It felt like an imminent danger. Einstein now faced a conflict of principles. Silence protected his pacifism. Action risked fueling the arms race. But to do nothing while Hitler's government might gain nuclear weapons first seemed worse. The choice pressed hard. Should a scientist committed to peace keep to principle, or should he use his authority to warn of an even greater threat? In 1939, fellow physicists approached him with urgency. They feared delay. They drafted a letter to the American president, but it needed a name powerful enough to draw attention. Einstein agreed and signed. The Einstein-Szilard letter, as it became known, warned the U.S. government that Germany might develop a bomb and urged acceleration of American nuclear research. That signature carried weight. Although Einstein did not construct the technical case, his name linked the warning to credibility. The letter found its mark. It helped set in motion what became the Manhattan Project, the vast secret program to create nuclear weapons. Einstein himself was never part of that effort. His security clearance was judged questionable, and his own reluctance kept him distant. He continued teaching and publishing, but not in the laboratories that built the bomb. Still, the connection held. His equation, E equals mc squared, stood as the theoretical underpinning, and his letter stood as the political spark. When the bombs were dropped on Hiroshima and Nagasaki in 1945, his quiet warning had grown into devastation. Cities faced destruction never before seen. Tens of thousands died in a split second. Einstein read the news with despair. He later said, "The time has come now when man must give up war. It is no longer rational to solve international problems by resorting to war. The comment reveals where his mind settled. He did not deny the direct role of physics in the new weapons. He recognized that his formula had laid the groundwork. Yet he insisted that the real challenge now was not scientific, but human. If war once escalated with rifles and trenches, it had now escalated to species-level risk. Nuclear conflict posed not victory or defeat, but annihilation. His regret grew clear in the years that followed. Asked about his part, he admitted moral unease, even guilt. He had signed the letter to prevent Nazi victory, but the same act helped empower the weapons used by his new home country. The paradox never eased. For a man who once called war a disease, to be linked by history to the atom bomb felt like living with a scar no recognition could heal. So he turned his energy toward preventing further disasters. In public and private circles, he advocated for international cooperation, even a system of global governance that could diffuse conflicts before force became option. He pressed for controls on nuclear weapons, arguing that the destructive scale required a new kind of political structure. Nations could no longer afford to act purely on self-interest when weapons of such magnitude sat within reach. To explain the urgency, he returned to simple images. He warned that humanity had entered a new age like an apprentice handed explosives without training. Without restraint, without cooperation, the result would be catastrophic. His voice joined others who called for abolition of war itself, framing it not as an idealistic wish, but as a rational necessity in the nuclear era. For Einstein, the irony was heavy. Decades of equations on energy and mass had described the interior of stars. Now, the same ideas burned into the statistics of human lives. The leap from abstract physics to political tragedy showed how science could not live apart from the world that applied it. To this day, his role remains debated. Was he complicit by warning America, or responsible only for the insight that energy and mass interlock while others weaponized it? These questions persist because he himself carried both strands, pacifist by creed, yet tied by act to the birth of the bomb. The episode marks the turning point when Einstein's science intersected with war. It reminds us how knowledge can shift from equations on paper to decisions shaping nations. And it explains why, for the rest of his life, Einstein spoke not just as a theorist of space and time, but as a man calling humanity back from the edge his own science had revealed. Can the deepest laws of reality be random? Einstein refused to believe it. For him, disorder at the core of nature seemed unthinkable. He trusted in underlying rules, steady and precise, guiding everything from the orbit of planets to the swing of a compass needle. But by the mid-1920s, the young field of quantum mechanics had made a radical proposal. At the smallest scale, particles did not follow definite paths. Instead, they existed in blurred states of possibility, and only when measured did one outcome emerge. That picture unsettled Einstein from the start. Quantum theory worked. Experiments with atoms and electrons confirmed strange behaviors that no classical theory could explain. Spectral lines, chemical bonds, radioactive decay, quantum rules predicted them correctly. But success did not guarantee comprehension. The cost of this predictive power was certainty. Instead of a clear line from cause to effect, researchers spoke of probabilities. An electron could be here or there, a photon could pass or reflect. Yet, until measured, the particle occupied a range of potential states. It resembled a dice roll at the universe's core. To Einstein, that metaphor felt wrong. He believed in an order waiting to be uncovered. His phrase became famous: "God does not play dice with the universe." The words captured his refusal to accept probability as foundational law. For him, probabilities hid ignorance, like weather forecasts, hiding details of each molecule of air. If we had a better map of causes, he argued, the apparent randomness would collapse into certainty. The debates sharpened at gatherings of the world's leading physicists. At the Solvay conferences in Brussels, he and Niels Bohr became the opposing poles of the argument. Bohr defended quantum mechanics as complete, embracing uncertainty and insisting reality itself behaved this way. Einstein challenged him, bringing fresh thought experiments to every session. These exchanges became legendary, quiet at times, forceful at others, always circling the same question: was quantum mechanics the final word or only a first draft? One of Einstein's recurring tools was the thought experiment, a scenario imagined carefully enough to expose contradictions. Suppose two particles interact, then separate far apart. Quantum theory claimed their states remained linked, entangled, so that measuring one instantly fixed the state of the other, even across distance. Einstein found that intolerable. For him, locality mattered. Physical causes should not leap across space faster than light. If quantum mechanics required such instant, distant effects, then something in the formalism was missing. Bohr countered that Einstein misunderstood, pointing out that entanglement was not a signal carried across space, but a correlation written into the joint state of the system. The license to think in terms of definite properties before measurement did not exist. Bohr's insistence was subtle, but unyielding. Quantum mechanics did not describe hidden reality beneath observation. It described what could be observed itself. To help the listener imagine the clash, picture two watchmakers. Einstein believed each gear was set and turned independently, with predictable results if we knew the full machinery. Bohr argued that some gears could not be described apart from the whole clock. They had no independent state until the mechanism acted. Einstein returned again and again to the first picture. Bohr stood by the second, and colleagues watched the tension elevate physics into philosophy. The Copenhagen interpretation, supported by Bohr, Heisenberg, and others, placed probability at the heart of reality. Particles had no fixed path until measured. Einstein's questions could not dislodge its effectiveness. Measurements kept matching the predictions, yet his resistance had value. Each objection forced sharp clarifications. Without Einstein's probing, the defenders of quantum mechanics may have left their ideas vague. His insistence on consistency strengthened the framework even as it resisted his approval. At the center of his resistance was simplicity, a deterministic world where cause and effect lined up without gaps felt both sensible and elegant to him. The probabilistic picture looked messy, unseemly. For someone who sought a final unified theory combining gravity and electromagnetism, conceding randomness was like leaving a crack in the foundation. His discomfort was deep, not tactical. The broader community, however, saw utility as decisive. Quantum mechanics predicted and controlled phenomena from chemistry to electronics. By the 1930s, engineers and experimentalists relied on it, whether or not they embraced its oddities. In practical terms, Bohr's probabilistic stance carried the day. Yet Einstein's counter-arguments became part of the scaffolding. New generations continued to ask if hidden variables might exist, or if the indeterminacy of the quantum world pointed to future, deeper laws. The Einstein-Bohr debates remain vivid in the history of science because they expose the gap between description and understanding. It is one thing to calculate outcomes. It is another to say what reality is. Einstein believed reality was definite, whether observed or not. Bohr asserted that our description had limits, that the act of measurement was part of physics, not external to it. The clash was not resolved in those years. Echoes of it continue in research today, from studies of quantum information to interpretations of entanglement. Surprisingly, Einstein's doubts also helped spark deeper explorations into entanglement itself. Researchers later designed experiments to test whether hidden variables could reproduce quantum predictions. These tests, built many decades later, showed correlations stronger than any local model could allow. Ironically, the very paradox Einstein used to reject quantum mechanics inspired experiments that confirmed its strangest claims. His resistance had pushed the field into territory it might otherwise have left untouched. Think again about that famous remark. God does not play dice with the universe. It was not a statement of theology, but of conviction. It announced that randomness could not be the lowest layer of nature. Some hidden order must exist, even if theories so far had failed to uncover it. For Einstein, the ultimate theory would harmonize all forces under fixed rules, not scatter them into probability clouds. The conferences in Brussels symbolized that divide. Picture the room filled with luminaries, arguments unfolding late into the night, diagrams sketched, counterexamples proposed. Among them sat Einstein and Bohr, circling again over the same riddle: determinism against probability, locality against entanglement, definite states against measured outcomes. Though the mathematics favored Bohr, Einstein's challenges kept the discussions alive and rigorous. From our viewpoint today, the debates had no final victory. Bohr's probabilistic framework still drives quantum technology, from semiconductors to lasers. But Einstein's demand for a deeper foundation remains a live question. Physicists exploring quantum gravity, hidden variable models, and cosmology echo his suspicion that randomness is not the ultimate story. His stance endures as intellectual resistance, a reminder that even successful theories invite further questions. Why does this matter to us? Because it shows science as more than a list of formulas. It is an argument over reality itself. To accept indeterminacy is to accept that the world at its base holds chance. To resist it, as Einstein did, is to insist there are rules we have not yet seen. Non-specialists may think the debate was arcane, but the implications touch philosophy, engineering, even our everyday grasp of what is real. In the end, Einstein lost the battles of consensus, but he shaped the landscape for all who came after. His doubts sharpened definitions, his thought experiments tested boundaries, and his determination kept the discipline honest. His refusal to accept probability as final truth turned out not to block progress, but to force it toward greater clarity. That is why even now, when physicists discuss hidden variables, the completeness of quantum descriptions, or the meaning of entanglement, Einstein's voice echoes as part of the conversation. The dice, in one sense, did roll, but the challenge he posed ensures we never stop asking if behind the roll lies a deeper mechanism. The questions he raised at those tables in Brussels remain, and to this day, they shape how we think about the strange, unsettled fabric of the quantum world. What did Einstein do when he wasn't bending space and time? He picked up a violin. Music was not a side interest or a performance skill to show off. For him, it was a private language, a way to think and relax outside the world of equations. He began the violin as a child and kept it with him through every stage of life, home after home, country after country. The instrument rested across his shoulder when ideas pressed too hard in his head. In sound, he found rhythm, a method different from chalk and paper. The act of playing mattered as much as the notes, bow to string, vibration to air. This process gave him a path into problems that logic alone could not untangle. Many times, when stuck on a calculation, he stopped not to force through with pen and ink, but to turn to Beethoven or Mozart on the violin. Melody brought order where equations seemed blocked. Music shaped his problem-solving rhythm just as much as mathematics shaped his theories. Inside his homes, music stood out more than furniture. Visitors often noticed the absence of wealth or ornament. Rooms were plain, modest, even bare. But a piano or violin was always present. They were the real centerpieces, hinting at his true indulgence. For someone who achieved global fame, he showed remarkably little interest in material possessions. The lavish item in his life was not a car, not clothing, not a mansion, but an instrument. He cared less about appearances and more about continuity in listening and playing. And yet, outside that music, conflict ran across his personal life. His first marriage with Mileva Maric held both inspiration and strain. She was a physicist as well, and there is evidence she joined in conversation about his work. But their relationship, marked early by challenges, also held complications around family. They had a child before marriage, and rumors about the fate of that child remained part of their story. Even after formal marriage, tensions surfaced. Collaboration in thought mixed uneasily with the pressures of family responsibility. Genius at the blackboard did not guarantee harmony at the table. His second marriage brought companionship of a different kind. Years later, he married Elsa, a cousin who provided stability after he moved to Berlin. With her came her daughters, and Einstein became a stepfather of sorts. But even this second home was not free of distance. His dedication to thought often made him detached. Work and public duties sometimes overshadowed personal connection. Elsa offered support, yet the marriage carried strains familiar from the first, this time less about shared physics, more about his tendency to turn inward. Complicated, too, were his ties with children. With Maric he had two sons, Hans Albert and Eduard. After separation, they remained with their mother. Einstein kept in touch through letters, but visits grew rare. Later, after his move to America, the split widened. Eduard fell into psychiatric illness in adulthood and lived in care. Einstein and Eduard never saw each other again in person after Einstein's emigration. With Hans Albert, there was eventual reconnection, especially after Hans Albert himself came to America, but even then, the relationship bore the scars of long separation. These family bonds remained complicated, marked by affection, regret, and distance. This side of his story shows the cost of the sort of focus that drives groundbreaking thought. Hours spent tracing invisible shapes of space-time or considering hidden laws in atoms left less for ordinary presence in family life. Einstein lived with human weakness as much as towering intellect. Wives, sons, stepdaughters all carried the weight of his divided attention. The pattern reveals how brilliance and humanity overlap, sometimes uneasily. Contrast deepens when we set these struggles against his public image. To the world, Einstein appeared a humble sage, friendly, smiling, disheveled, walking to work without care for clothing or wealth. He looked approachable, grounded in simplicity. Yet behind closed doors, life was complicated, sometimes painful, stretched across failed marriage and fractured relationships. He was far from the caricature of pure genius untouched by ordinary flaws. Humor coursed through his personality as well. Even amid stress, he carried wit and light irony. Friends told of his jokes, often dry and tinged with self-mockery. Those jokes made him feel accessible to others. Paired with his modest way of living, the humor helped prevent him from becoming too remote in the public eye. His blend of humility, wit, and indifference to material status made him popular in ways beyond science. He looked not only brilliant, but also slightly eccentric, the absent thinker who nonetheless smiled at simple amusements. Returning to the music, this pattern of balance becomes clear. As equations pulled his mind toward abstraction, the violin returned him to the body, fingers on strings, bow against resistance, ear tuned to harmony. This grounded him. In tone and rhythm he found release from pressure and a space to reorganize thought. Playing did not distract him from science, but became a lateral form of thinking. When problems seemed too sharp, music softened them into shape. Think of two parallel tracks. On one, tense relationships, estranged children, absent father moments. On the other, achievements unmatched in his century. The link between the tracks was music. It served as the bridge that let him sustain both. Without that discipline of sound and rhythm, the strain might have broken him sooner. His violin was as much a tool as any chalkboard, and perhaps more vital to his sanity. What emerges is not a saint or a machine, but a man of contrasts. He achieved world-changing science while stumbling through fragile personal ties. He displayed humility in lifestyle, but lived complications at home. He rested in music, but carried regret about family. All of these together formed his story. Genius did not erase humanity. It made the tensions sharper. For us, the payoff is a fuller picture. Beyond relativity, beyond equations, and the physics that reshaped modernity, Einstein stood as a human being with all the weight of flaws, loves, and disappointments. He laughed, he played music, he failed as a husband, he grieved as a father, and he inspired as a thinker. To hold the violin in his hand was to show that the same person who redrew time itself still turned to melody to find balance in daily life. In this light, we no longer see Einstein as a detached figure only of equations. We see a human portrait, curious, flawed, witty, humble, someone capable of profound insight and of ordinary mistakes. His violin, his modest home, his broken marriage, and his strained yet real love for children complete the picture. It shows us that genius can coexist with struggle and that even the greatest mind of the century lived a life marked by human contradictions. Every time you check your phone's GPS, Einstein is there, silently correcting your clock. It may seem like an ordinary tool of modern life. Open a map app, follow the blue arrow, but below the screen, relativity is at work. Each satellite orbiting above Earth carries an atomic clock, counting time with remarkable precision. Yet those clocks would drift from the ones on Earth if left unchecked. Why? Because time itself runs differently in orbit than it does here on the surface. Special relativity tells us that moving objects experience time slightly slower. General relativity adds that gravity slows time as well. A clock on the ground deeper in Earth's gravity ticks a little slower than one circling high above where the pull is weaker. Add the orbital speed of the satellites, and the mismatches become large enough to wreck the entire system. If no corrections were made, the GPS you rely on would be wrong by several kilometers after just one day. So each time you use a navigation app, you benefit from adjustments rooted in Einstein's theories. The satellites constantly apply relativistic corrections, small on a human scale, but crucial for accuracy. This makes GPS one of the most direct, everyday examples of how relativity shapes life for billions of people. What once looked like abstract mathematics now guides cars on highways, planes across oceans, and hikers through mountains. But GPS is only one strand of Einstein's influence woven into technology. Another comes from his famous equation, E equals mc squared. It revealed that mass is stored energy. This insight underpins nuclear power plants. By splitting uranium atoms, matter is transformed into heat, releasing energy millions of times greater than any chemical reaction could provide. That energy boils water, spins turbines, and lights homes. Every kilowatt from a nuclear plant is a direct consequence of Einstein's linkage between matter and energy. The same equation led to something darker, nuclear weapons. When small pieces of mass convert into energy, the release can arrive in a fraction of a second as blinding light and destructive force. Einstein regretted this outcome, but it shows the raw power of a principle so simple in appearance. Mass and energy are interchangeable forms. The dual legacy of E equals mc squared is clear: electricity in peaceful use, destruction in war. His work on the photoelectric effect also lives inside tools around you. When light strikes certain materials, electrons are freed, flowing as current. The principle explains why a solar cell can turn sunlight directly into electricity. It also powers the automatic sensors that switch on streetlights at dusk or awaken solar calculators with daylight. The photoelectric effect, once just a puzzle of light, became the seed for practical energy technologies. Think of Einstein's contributions like a hidden root system. Above the ground you see trees of modern life, navigation, nuclear power, solar energy. Below lies a network of insights he uncovered. Each application grows from those roots, though most people never pause to connect the leaves they use every day to the deep physics that feeds them. Consider again GPS. Without relativity, it would collapse quickly into uselessness. Cars would miss turns, airplane routes would scatter, emergency services would lose precision. Cities depend on it for transport, logistics, even banking transactions that rely on synchronized time stamps. Each function rests on Einstein's equations of space-time. Without them, the global economy would stumble. And beyond technology on Earth, his theories still guide space science. Relativity provides the framework for understanding black holes, the regions where gravity curves space-time so tightly not even light can escape. It also explains gravitational waves, ripples spreading from violent cosmic events. Instruments detect these waves by watching stretches of space shrink and expand by less than a width of an atom. That ability to measure such tiny shifts rests on equations written by Einstein over a century ago. His equations also remain central to cosmology. They describe the expansion of the universe, the bending of light from distant galaxies, the time dilation seen in cosmic observations. Astronomers rely on them daily when charting the cosmos. Without relativity, modern astrophysics would have no foundation. Yet, despite these immense contributions, few realize that we touch his legacy each time we use technology. The man seen as a symbol of pure theory ended up shaping the most practical of tools. He is not just a figure in textbooks or photos with unruly hair. He is built into the infrastructure of satellites, sensors, and power grids. Think of it as a hidden engineer at work in the background. Every second, relativity corrects satellite clocks. Every day, nuclear plants convert matter to energy. Every night, lights flick on, powered by sensors designed with the photoelectric effect. Einstein is there, not as a face but as a framework, directing systems modern life depends on. The irony is striking. He pursued questions not for utility, but for curiosity. How does light behave? What is time? What binds energy to matter? Yet those very questions led to answers that built industries. His fingers never twisted a satellite wire or bolted a turbine, yet his ideas drive them. Curiosity, refined into theory, became architecture for civilization. The consequence is that Einstein's legacy is not locked in history. It continues to operate minute by minute, layered into how systems run. As we advance into quantum computing, nuclear fusion research, and deep space travel, his theories form the base upon which new work grows. Each generation builds on foundations he set. It is easy to picture him as disconnected from practicality, sitting aloof with equations. But his work flowed outward in ways that prove abstract thought can become concrete structure. The chalk dust of relativity became the steel of satellites. The idea of the photon became the silicon of solar cells. The equivalence of mass and energy became both electricity in the grid and fire in cities. His reach extends from the cosmos down to the phone in your pocket. This is the quiet legacy. Einstein did not just redraw the map of science. He hardwired his equations into the circuitry of modern society. From navigation that saves lives to cosmic theories that expand curiosity, his influence lives continuously inside the systems around us. Far beyond classrooms and thought experiments, his ideas built the backbone of modern life. Even after reshaping physics, Einstein spent decades chasing a theory he never found. By the late 1940s, in his office at Princeton, he turned his full attention to what he called a unified field theory. He sought one framework that could combine all known forces into a single description, showing gravity and electromagnetism as different faces of the same foundation. If you imagine the universe as machinery, his earlier theories had already explained some of its gears. Relativity accounted for gravity by showing how mass curves space and time. Electromagnetism explained light, radio waves, and the forces binding electricity and magnetism together. But they lived in separate towers. A true unified theory, Einstein believed, would reveal the base they both rose from. He published an outline of this work in Scientific American in 1950 under the title On the Generalized Theory of Gravitation. It was part presentation, part invitation. His paper described how curvature might not just account for gravity, but could also bring electromagnetic fields into the same mathematical fold. For him, this was the logical next step, to press further until everything, from falling apples to glowing stars, fit under one coherent framework. But science had changed around him. While Einstein pursued elegance, quantum mechanics had taken the field in another direction. Its models, despite their probabilistic nature that he distrusted, were producing unmatched results. They explained the structure of atoms, why elements bond, how semiconductors work. Laboratories around the world built experiments that confirmed quantum predictions with precision. Einstein, however, continued to mistrust its foundation. He saw quantum mechanics as useful, but incomplete, a temporary set of tools hiding deeper rules underneath. At Princeton, year after year, he explored new versions of his theory, refining equations in search of a unifying principle. Many of his colleagues admired his persistence, yet the field itself drifted toward quantum applications. He was respected, but increasingly isolated. The image of Einstein at this stage is striking. While younger colleagues tested nuclear forces in accelerators or advanced solid-state physics in labs, he sat with pen and paper pushing geometry into new forms. He believed mathematics, carefully shaped, could still reveal the hidden connections. His method was consistent with his entire career: question the foundations, simplify where possible, and trust nature to prefer elegant rules. But did this persistence mark stubbornness or foresight? Some judged him as hunting a mirage, unwilling to accept that physics had grown more probabilistic, untidy, and resistant to final closure. Others saw him as ahead of his time, pointing toward a synthesis that would become the dream of future generations. The truth may lie between. His calculations did not bring consensus, but the very vision of unification still drives research today. To picture his quest, think of an engineer standing before two great bridges built across a river. Each bridge works well on its own, but they rise from different banks and never meet in the middle. Einstein believed that, somewhere under the water, a hidden foundation joined them. He wanted to prove the bridge was already there, waiting to be revealed. His unified field theory was his way of diving beneath the surface to see what connected the supports. Yet the details of his approach often disappointed peers. His equations grew intricate, but detached from experiment. Physics was shifting toward theories that were less about elegance and more about testable predictions. Accelerators, cloud chambers, and spectrographs demanded models that matched their data. Einstein's work, by contrast, remained abstract, difficult to connect to measurement. He submitted articles refining his unified idea, but they found limited traction. Journals published them out of respect, yet results did not spur waves of follow-up. The landscape of physics now included nuclear forces, weak and strong interactions, which his framework did not encompass. What began as a bid to unify two great forces fell short as more were discovered. Each new force made his system less inclusive, not more. As the years wore on, Einstein acknowledged the difficulty but did not abandon the hunt. To the public he remained the symbol of genius, but to many scientists he appeared unwilling to engage with newer approaches. Still, younger researchers recognize that his ambitions, if not the specifics of his calculations, kept a powerful question alive. Could all fundamental forces be described by one theory? And that is where his legacy in this area lies. His pursuit directly advanced mathematical tools, particularly in differential geometry, the study of smooth shapes and continuous surfaces. Modern attempts like string theory and other routes toward quantum gravity inherit his central ambition. They too try to show that gravity and quantum forces spring from the same origin. They too seek a framework that does not split natural law into compartments. Every generation of physicists who picks up the unification problem stands, in part, in Einstein's shadow. What makes his pursuit compelling is not whether he succeeded, he clearly did not, but how it illustrates the scientist's mindset. Even after revolutionizing how we see light, space, and time, he believed large questions remained. He did not rest on earlier discoveries. He kept returning to the sense that nature must be simple at its core, that the apparent complexity of forces could be traced to one reality. In his later decades at Princeton, he was often seen walking slowly, thoughts inward, scribbling calculations at his desk, persisting against indifference. That persistence itself is part of the story. It shows the will to keep pressing when the tide of consensus flows the other way. It also shows the danger of focus. His refusal to take quantum theory fully on board left him isolated, admired, but set apart. So we face a paradox. His great idea was unfinished. His specific unified field theory faded, folded into archives. Yet the quest itself remains alive. Today's physics still pursues grand unification, still asks whether space, time, matter, and energy can be described by a single law. Einstein's failure, then, is not absence of value. It is continuity of challenge. It's seeded work that continues to this day, inspiring others to seek what he could not. The search reflects one of his deepest convictions. The universe is not a patchwork, but a whole. And somewhere, hidden still, lies the theory that proves it. Einstein transformed an ordinary desk job into the greatest revolution in science. At a patent office table, routine reviews became launchpads for ideas that reshaped reality. His lesson runs deeper than formulas. Discovery can grow from overlooked spaces, from attention to details others dismiss. He once said, "I have no special talents. I am only passionately curious." That curiosity was his true inheritance to us. It proves persistence and imagination matter more than circumstance. He didn't just change science. He changed how humanity sees reality and how you and I imagine what might be possible next.